Hi class. I want to continue with our examples of using the calculus of residues to evaluate real integrals. Next I want to consider a case of an integral that involves a function with a branch cut, the square integral of the square root of x over 1 plus x squared from 0 to infinity. So again, our function, as a function of a real variable x, is the square root of x over 1 plus x squared. The obvious analytic continuation of this is the square root of z over 1 plus z squared. However, viewed as a complex function, this function has a branch cut starting at z equals 0, because if we circle the origin, the square root changes sign. We're going to choose this branch cut to run from the origin along the real positive axis. And that corresponds to saying that we're defining an angle, theta. If we have any arbitrary z in the complex plane, we have a radius r and an angle theta, where theta runs from 0 to 2 pi. So implicitly, by drawing the branch cut like this, I define what I mean by the argument of any complex number z, and that tells me how to evaluate the square root. If I evaluate f at r e to the I theta, some arbitrary z, I get the square root of the real number r, which is positive, e to the I theta over 2, over 1 plus r squared e to the 2I theta. So by unambiguously defining theta, I unambiguously define my function, and it corresponds to this branch cut. So, having defined it this way, if I think about going to the real axis just from above, so if I want theta equals 0, which is sort of in this range here, then by definition, theta equals 0, and so if I evaluate f of z agrees with what I mean by the real value of the function, square root of x over 1 plus x squared, just above the cut. On the other hand, if I approach the real axis from below, then z is x e to the 2 pi I, because theta is 2 pi I there, which means square root of z is minus square root of x. Sorry, there should be a square root there. Minus square root of x. So if I think about evaluating the function from below, I get the negative of that, minus square root of x over 1 plus x squared. So if I look at the value of the function just above the cut, I get the real function that I'm interested in. If I look at it just below, I get the negative of that. So that's actually presents an interesting opportunity. Let me consider the following Pac-Man contour, like the Pac-Man video game, if you remember that. I'm going to take a contour starting just above the real axis, infinitesimally above, going out along the real axis to infinity, circling all the way in the complex plane, all the way around. But since the plane is the cut plane, I can't go all the way back. Instead, I have to come back along the real axis, but now just below, and then I have a small circle just around the origin. So I don't actually go through the origin, but I go arbitrarily close to it. Let me think of this contour as being divided into L1 and L2, the straight pieces going out and coming back, first above and then below the real axis. The contour is C2 at infinity, and the contour is C1 very close to the origin. Well, the piece from C2, as I take the radius of this contour, goes to infinity, because this function falls like 1 over the distance to the 3/2 power. So here's an example where, the length of the contour is r. So as I take r to infinity, the magnitude of f of z goes to 0 like 1 over z to the 3/2. So the whole contour, the integral of the whole contour goes to 0. Similarly, if I take an arbitrary circle of radius epsilon near the origin, that also goes to 0, because the magnitude of the function is just the square root of epsilon there, because the x squared in the denominator becomes arbitrarily small. So the magnitude of the function along the contour, and in fact its length, also goes to 0. So both the contributions from the contour at infinity and the contour close to the origin vanish. That means if I do this integral along this whole Pac-Man contour, all I get is in the limit where I take the radius of the outer contour to be infinity and the radius of the inner contour to be 0, I get the integral I want, the integral of L1, which is just the square root of x over 1 plus x squared. But then I have the integral coming back. That's the integral from infinity to 0, but of minus the square root of x over 1 plus x squared. But notice the minus sign here from the change, the discontinuity in the function across the branch cut, exactly cancels the minus sign we need to flip the order of integration. So the integral around this whole Pac-Man contour gives me twice the integral I'm interested in, twice the integral from 0 to infinity of the square root of x over 1 plus x. Putting this all together, the integral around the Pac-Man contour, which is twice the integral I'm interested in, is 2 pi I times the sum of all the residues inside the Pac-Man contour. Well, the residues inside, the square root of z over 1 plus z squared, has simple poles at z equals plus or minus I. And the simple pole at z equals plus I is the numerator, the square root of I, divided by the derivative of the denominator. The derivative of the denominator is 2z, evaluated at I gives me 2I. I have to be careful to evaluate this square root according to the prescription I have with the branch cut. So theta above in the positive imaginary axis with the prescription I've taken is I pi over 2. So this gives me e to the I pi over 2 to the 1/2 divided by 2I. So this is the residue. Similarly, along the negative real axis, the other simple pole at minus I, by the definition of theta that I use to define the square root, that's 3 pi over 2. So I get the square root of 3I pi over 2 divided by minus 2I, that is the derivative evaluated of the denominator evaluated at minus I pi. So this gives me that residue. If I add these residues together, and I divide by 2 because the integral over the Pac-Man contour is twice the integral I'm interested in. Therefore, pi I times the sum of the residues gives me the value of the integral I'm interested in, which is pi over the square root of 2. Again, it's nice that this is real. It wasn't entirely obvious through all of these calculations that all of the i's would cancel, and this I here at the end was crucial. And the value of the integral is real, and it's positive, as we know it must be. The fourth example of an integral that we're going to use contour integration to evaluate is of an entirely different kind. The integral from minus infinity to plus infinity of e to the plus ax over 1 plus e to the x dx, where a is a positive real number strictly between 0 and 1, both greater than 0 and less than 1. The reason that's important is that allows this integral to converge. As x goes to plus infinity, the e to the x in the bottom dominates, and the whole thing goes to 0 like e to the a minus 1 times x, so a has to be less than 1. As x goes to negative infinity, the e to x in the denominator becomes irrelevant, and the whole thing goes to 0 like e to the ax, where x is going to negative infinity, so that also goes to 0 as long as a is greater than 0. So the analytic continuation here is clear. We take f of x, which is e to the ax over 1 plus e to the x. We analytically continue to e to the az over 1 plus e to the z. This function, remember the exponential function, when you think of it in terms of real variables, we think of it as never vanishing. But in terms of complex variables, it does vanish because e to the I theta is cosine theta plus I sine theta. And whenever we can take e to the z equal to negative 1, we will get a pole. And in fact, just by looking at it, if we take the derivative, the derivative won't vanish at the pole. So we have simple poles, but we now have an infinite number of them if we plot them in the complex z plane at I pi, 3 pi I, 5 pi I, and similarly negative pi I, negative 3 pi I. The integral that we're interested in is the integral along the real axis from negative infinity to plus infinity. We have to figure out how to take this contour along the real axis and turn it into a closed contour where we can evaluate things. Well, you'll notice something interesting. The exponential function is periodic along the imaginary axis. And if I come back along a line where the imaginary value of z is 2 pi, then everywhere along this contour, the z value is some real value x plus 2I pi, and e to that is just e to the x. So coming back, I can imagine making a big square where I go from negative infinity to plus infinity. I go vertically 2 pi in the imaginary direction, and then I come back from infinity to negative infinity, and then I close with a big square. And because of these limits here, the contributions from the ends, as I take this square to be infinitely, or rather rectangle to be infinitely large, the contributions from the ends vanish. So the integral along the curve is the integral along line 1, which is the integral I'm interested in, plus the integral coming back along line 2. The integral along line 1 is the integral from minus infinity to plus infinity e to the ax over 1 plus e to the x. But coming back, I go from plus infinity to minus infinity, and as I said, any value of z there is x, the real value, plus 2I pi, and I get e to the a times x plus 2 pi I in the numerator divided by 1 plus e to the x plus 2 pi I in the denominator. The 2 pi I here in the denominator is relevant, and the overall factor in the numerator, the e to the a times 2 pi I comes out to be an overall factor, plus I have a minus sign. If I want to combine these integrals, I can do so by flipping and making this the integral from minus infinity to plus infinity with a minus sign. So the whole thing, the integral along this huge rectangular contour, is 1 minus e to the 2 pi I times the integral from minus infinity to plus infinity of e to the ax over 1 plus e to the x dx. So that turns out to be 2 pi I, the integral along the contour is 2 pi I times the sum of the residues enclosed. The only residue is the only pole enclosed is at pi I, and we just argued that it was a simple pole. We can evaluate it by taking the numerator times the derivative of the denominator. Again, that only works for a simple pole, but as we see over and over again, that's a very common situation. So I get 2 pi I times the numerator e to the a pi I divided by the derivative of the denominator e to the pi I, and that gives me this contribution here. Finishing up then, we have overall that the integral we're interested in is the 2 pi I times the residue, which we've just computed, divided by the overall prefactor relating the square contour to the integral I'm interested in, 1 minus e to the 2 pi I a. And with a little manipulation, you can see that this is pi over sine pi a. Again, we've been able to show that the integral is real, which is good, because that's the value we should have gotten. Also, you can see that it has the right behavior. If a goes to 1 or to 0, we know this integral should diverge. And if a goes to 1 or 0, the sine pi I in the denominator diverges. So this integral has exactly, the evaluated form of the integral has exactly the properties that we believe the integral has itself.